Moore's law was a prediction made in 1975 by Gordon Moore that the number of transistors on a silicon chip would double every 2 years. Now, a microchip is an interconnected pattern of transistors on a silicon chip, and the transistor is the functional unit of the microchip. Silicon is the base of every microchip, but why silicon? So it's a semiconductor, meaning its conductive properties lie in between a conductor and an insulator. And to form a transistor, elements are added to the pure silicon lattice to control its number of free electrons. Phosphorus has 5 outer shell electrons compared to silicon's 4, meaning when it is introduced into the lattice there is 1 free electron. Therefore this is called negative type silicon, and this type of lattice supports conduction depending on the voltage applied to the material. Boron has 3 outer shell electrons, meaning its silicon lattice is 1 electron short, producing positive type silicon. This process of adding small amounts of other elements to a silicon crystal is called doping and is used to simulate an on-off switch at an atomic level. So other reasons why silicon is chosen, well, it's really cheap, it's the second most abundant element on Earth after oxygen, and it's very easy to manufacture. Silica sand, silicon dioxide, can be melted into a cylinder, and that forms a pure silicon ingot, which can then be sliced to about 0.5 millimeter thick. These slices are called silicon wafers, and like the one above, they're then cut down into individual square chips, ready to be placed on your phone or computer. So how are chips made? Well, have you ever heard of ASML? They are probably the most important tech company that you've never heard of. They make the big machines that make the small chips we use every day. The machines weigh over 180,000 kilograms and cost £92 million and are bought by companies such as Intel or Nvidia, and they use them to manufacture their chips. So the first step in the manufacturing process is to coat the wafer with a thin film of conductors, such as phosphorus and boron, as we've seen. Then they use a technique called photolithography to print a layer onto the silicon chip. This is the most critical step in the chip manufacturing process. First, the surface is coated in a light-sensitive material called a photoresist, and light is projected through what's called a reticle, which acts as a kind of blueprint for the design of the chip. So this pattern of light then lets through this print and imprints it on the wafer. So after photolithography, the wafer is then baked and developed, and then the gaps between the different layers in the chip are etched away to give a 3D lattice. This whole process just repeats itself and just creates one layer onto the wafer. So it's repeated 100 times to produce the average chip with 100 layers. So after the last 50 years, this process has been tweaked over and over again to increase the size of to increase the number of transistors on a chip. So shrinking the size of the transistor is required to keep up with Moore's law. This equation, the Rayleigh Criterion, describes how small the features on a chip can be printed using lithography. The CD represents the critical dimension of the chip, or the smallest possible feature size that can be printed on the chip. So that's the thing that we want to minimize. Lambda is the wavelength of the electromagnetic light used in the photolithography process. N sine theta just represents the numerical aperture of the machine's optics and mirrors. And then K is a constant representing lots of other factors in the chip manufacturing process. So as we can see, there are 3 main ways to reduce the critical dimension of a chip. There's tweaking the lithography process to decrease the K factor. There's increasing the mirror aperture to collect and focus more light on the wafer, or decreasing the wavelength of the light used. Now, this final option has been the cause of the majority of breakthroughs in the chip manufacturing process in the last 50 years, and it's been the focus of ASML. So when it was founded in 1984, ASML used a light source from a Mercury Vapour lamp. Now, Mercury lamps produce light by passing through electricity through a bulb containing mercury, and the current vaporizes the mercury into a high-energy plasma. And the excess energy is then released as a spectrum of light. So they would then use an interference filter to select light with a wavelength of 436 nanometers to be used in photolithography. And that's a visible blue light, and printed a critical dimension of around 1,000 nanometers when it was used. Mercury eyeline lamps were then developed to instead filter all but invisible ultraviolet light with a wavelength of 365 nanometers. So this pushed the critical dimension to 220 nanometers. Then, in 1990, ASML decreased the wavelength of light by using deep ultraviolet excimer lasers. Now, excimer lasers combine an inert noble gas, such as krypton, with a highly reactive element, such as fluorine, and at high temperatures, these elements bond to form krypton fluoride, and it's in a very excited state, so the molecule releases its excess energy in the form of ultraviolet light with a wavelength of 248 nanometers. So that shrunk the critical dimension of the chip further to 150 nanometers. Today, argon fluoride excimer lasers are used to produce light with a wavelength of 193 nanometers, and this is used to produce more cost-effective microchips. Now, to reduce the wavelength of light even further, ASML now use extreme ultraviolet lithography, which is a process entirely unique to them. So their extreme ultraviolet light has a wavelength of 13.5 nanometers. Now, to put that into perspective, this is the electromagnetic spectrum, and X-rays, as you can see, start on the left of this diagram at a wavelength of 10 nanometers. So the critical dimension of chips that extreme ultraviolet light can produce is about the width of 25 atoms. Now, to produce extreme ultraviolet light, an even more ridiculous process is required than what we've already seen. Firstly, a drop of molten tin, you can see a couple there, are dropped into a vacuum at 70 meters per second. Now they're about 25 micrometers in diameter. They're then flattened into a flat kind of pancake shape by a laser, and then they're vaporized by an industrial megawatt laser amplified 10,000 times. And it's this tin plasma which releases the extreme ultraviolet light. This specific process is repeated 50,000 times every second to produce enough light for the lithography process. So the ultraviolet light produced by the tin is then collected and focused on the wafer. So first, a parabolic mirror called an illuminator collects the light from the tin, and it's about 1.2 meters high and weighs about 1 metric ton. Now, specifically, it's a mirror, not a lens, as a lens would absorb most of the light instead of reflecting it. However, the onslaught of ultraviolet light causes the mirror to heat up, causing distortions. So sensors measure the temperature changes in millikelvins and actively adjust the position of the mirror accordingly. This is called computational lithography and has decreased the wafer defect rate in recent years. The illuminator is also extremely flat. You may be wondering why there's a picture of Germany in front of you. Well, if the illuminator were the diameter of Germany, the highest equivalent mountain on the surface of the mirror would be just 1 millimeter high. And if that wasn't enough, the light passes through 8 more mirrors, and in the final stage of the optics is passed through water. Yes, water inside an electronic machine. It's called Immersion Lithography, and it increases the numerical aperture of the chip even further. Now, the light has reached the surface of the wafer, and the wafer is held on platforms called stages, which magnetically levitate to reduce friction. Each stage moves to focus the light on different parts of the wafer, and to do this they accelerate at 5G, that's the same as a fighter jet during takeoff. But it goes further. To keep up with the stage, the reticle above has to accelerate even faster at 15G to compensate for the movement of the stage. So, the wafer is now ready to be developed before the next layer. Okay, so this whole process takes place in a zero-dust environment to reduce the rate of dust-related defects. Operators wear these bunny suits to make sure there are no more than 10 particles between 100 and 200 nanometers in size that are allowed inside 1 cubic meter of air within the clean room. To put that in perspective, a modern hospital has around 10,000 particles per cubic metre. Well, there you have it, the entire chip manufacturing process. All of that to produce each of the 634 billion microchips made every year.